welcome back to the second part on Hausdorff distance. And we are starting always from this vector space Rd and the Euclidean distance. Okay, so the first property that I would like to mention here is that what if the Hausdorff distance between two sets A and B is equal to 0? Okay, if that's the case, then it implies that the closure of A is equal to the closure of B. And if both of them are already closed sets, A and B are already closed, then it means that they are equal. So two closed sets where the positive Hausdorff distance should be different. Okay, so that's the first property here. Another property that will be helpful later on is that if I take a number, a real number, positive 1, and I multiply it by the same number, the set A, and also by this number, the set B. Okay, so each vector in A and each vector in B, and I take the Hausdorff distance, okay, between these two sets, then it's going to be equal to lambda time the age A and B. Okay. And so that's the second property. The third one, okay, is basically not a property, or it's more a definition, okay, which says that if we have a sequence, A1, A2, and so on, of sets, okay, what does it mean that a set converges to another set? Okay, so we have this sequence, and we have another set A. Okay, then if so, we say that AN will converge to the set A in the Hausdorff sense. Okay, so the limit, which is a set, if, okay, so that's a definition, if the Hausdorff distance between AN and A, which is a number, will converge to 0. Okay, so that's the Hausdorff distance. There are other notions of convergence between sets, and very often, depending on the space that we are dealing with, but very often they are equivalent. So this is one that is defined based on our definition of the Hausdorff distance. Okay, great. There is an alternative definition for the Hausdorff distance. Okay, so we'll say that the Hausdorff distance, or we claim that the Hausdorff distance between two sets A and B, okay, can also be defined, or is equivalent to the smallest radius, okay, so the argmin, okay, over the number r, which is radius. It's going to be a positive 1, okay, such that if we take the set A, okay, and add to it, okay, Minkowski sum of a ball, and I'm going to use this script B and sub r, which is the ball centered at the origin with a radius r. It will be contained, okay, in the set B, and, okay, also B, if we take B and add to it this script B, which is a ball of radius r, is contained in A. Okay, find me the smallest radius, and it will be equal to the Hausdorff distance between A and B. That's another way to think about what the Hausdorff distance is. Let's think about some special cases. Okay, so if P and Q are convex polygons, okay, then to compute the Hausdorff distance between the Hausdorff distance between the polygon P and the polygon Q, okay, can be done in a linear complexity or computing time, which is depending on n plus m, where n is the number of vertices for polygon P, and M is the number of vertices for polygon Q. So computing, okay, so to the computation of this, okay, computing is O of n plus m. Okay, so that's very convenient. There are some packages for your favorite programming language that can do that. And I'll try to put some links in the comments or in the section below the video. Okay, so that's very useful. Okay, so now I'm going to move to some properties which, again, by and large, they can be maybe thought as properties of the Minkowski summation, but we will need the Hausdorff distance to make those claims. So first of all, the term that I want to define here is for set A, okay, convex hull of A is the smallest, okay, smallest in terms of inclusion, smallest convex set that contains A. Okay, so that's the conv. And the property that I want to write here is that the convex hull of A Minkowski sum B. Okay, so first I do the Minkowski sum and then I convexify it. That will be the same as taking the convex hull of A first and then summing it, Minkowski summing it to the convex hull of B. So the order of operation doesn't matter in this context. Okay. So again, that was purely about Minkowski summation, but we are building something here to get a very interesting result. The other concept that I want to define here is what is the radius. Okay, so for set A, okay, the radius of A, R of A, okay, is going to be the radius or the smallest radius of a ball containing A. Okay, so I will picture a ball and it will contain inside of it A, but if I up to the point where I can't make the radius of that ball any smaller without getting into the set A. Okay, so that's the definition of a radius, and now I'm going to use these properties to define or to state the important Shapley, Folkman-Starr theorem. Okay, it says the following: if we take a sequence of sets, okay, A1 plus Minkowski plus, okay, all the way Minkowski sum to AN, okay, and they are all in RD, okay, and then I'm taking in comparison the sum, again the Minkowski sum, okay, and now I'm going to write it in a more compact way. Okay, I'm going to do this operation. I goes from 1 to n, and I'm going to first convexify them and then sum them. Okay, so sum of the convex, and this is just the sum of the sets themselves. And I'm asking myself, how different is the sum from the sum of the convex hulls of the sets? Okay, so how different? Okay, so let's take the Hausdorff distance between them. Okay, and the Shapley-Folkman-Starr theorem says, and then there are several ways to write it, but I'm going to write it in a short, efficient way. It's less or equal to d time and this d is the same d here with the dimension, time the maximum over all the sets I of the radius. Okay, and in fact, as I said, there are shorter, or sorry, less generous upper bounds than that. But I want to make a point, and that will be enough for me to do. It's enough to sum the d biggest radiuses, but I said d times the biggest one. Okay, so what am I going to do with this? I'm going to first use the property number 2, and I say that dh, I'm going to multiply by 1 over n, and here I'm going to write this in a compact way as well. I goes from 1 to n of ai, right? And then I'm going to use the same 1 over n, okay? Minkowski sum, I goes from 1 to n of the convex hull of ai. Okay, so that will be by number 2 there less or equal to d over n, and again times the maximum over I of the radius of these sets. Great. Better, okay, I'm going to now multiply from the outside by root n. Okay, so root n times the dh of the Minkowski average. Okay, those can be called as Minkowski average of the sets versus the Minkowski average of the convex hull of these sets. And again, if by this one, by number 6, it doesn't matter if I take the average of the set and then convexify the average, or take the average of the convex. And here I need the summation. Okay, you will add here the summation from 1 to n of the convex sets. Okay, and again, since I multiply both sets here and here by the same constant, then I can, that was a here, but I'm multiplying from the outside. So this is still being less than d over square root of n times the maximal radius. And that's great, because as n goes to infinity, if the radius is bounded, then the expression on the right-hand side goes to 0. Okay, so asymptotically, okay, whether I average the sets or I average their convex hull is the same. Okay, so I can imagine that asymptotically, or it's as if I'm thinking that from the asymptotic perspective, I can basically treat A as convex, or just take the convex hull of them, and that will be the same. Okay, so these are the properties that I wanted to discuss in this second part and last part on the Hausdorff distance. Thank you for watching.